be sheared off. This portion will be sheared off from this point and from this point. So there will be double shear. So this is which kind of shear? Again, this is direct shear, as it is taking place because of the two equal and opposite forces. This will try to push it here and this will try to push it here. So applied force divided by cross section. Now what is the cross section? From this diagram, the cross section will be, now if you see this much distance, this much distance is, how much is that distance? For that you need to understand this. This is diameter d, this is diameter d0, right? So d0 minus d, we will get this much, and this much we have to divide it by 2, then we will get this much dimension. So what is the cross-sectional area? This cross-sectional area, that will be equal to d0 minus d divided by 2. So we have got this equation. We have got this multiply by thickness d1. So this is the area from one side subjected to shear failure, multiply by 2, as there are two shear area, double shear takes place from this side and from this side. So from this equation, d1 was known to us, d was known to us, d0 also we have calculated d0. So from this equation again we have to check safety of the design. So tau d is equal to SSY upon factor of safety. This is sigma allowable. We will calculate first this, then by putting all these known values we will calculate sigma, that is this is tau allowable, then we will calculate tau calculated from this value. So what we have to analyze is value of this parameter, that is tau allowable, has to be greater than value of this parameter, that is tau calculated. Then and then whatever dimension we have found it out are safe. If it comes unsafe, we have to change either the material of the component or we have to change the thickness which we have assumed with the empirical relations. There are two ways. Either we can select the maximum strength material or we can increase the dimension to have the safety of the design. Understand? So this is the shear failure of the single eye. Now why we are doing all this? We are making the component safer by doing stress analysis, by selecting the dimension based on empirical relation. So in case of quarter joint, we have found out all the equation by all the dimensions with the help of stress equation. In case of knuckle joint, we are assuming some dimension on the basis of empirical or past experience. By putting that values of that particular dimensions, we are checking the design for safety, and for the checking the relation for checking of the design is calculated value of stress has to be less than allowable stress for that particular mode of failure. Understand? Let's move ahead. The next type of failure is tensile failure of double eye. Now in case of tensile failure of double eye, let's consider this is knuckle joint. Now double eye means this portion which connects the two holes with the rod, and this will be subjected to the same kind of failure which the single eye was subjected to. Single eye first failed from the center, tensile failure, then crushing of the central portion with respect to pin, and then pin will try to shear off this single eye. Now last three failures are remaining for the double eye. So what are that failures? This double eye will try to get tensile failure. It will be break from the center due to tension. Second one is when this pin is mounted like this, it will produce a crushing on the pin or on the surface of the double eye, and when crushing gets increased, this pin will try to come out of the double eye. So first failure is a tensile failure, right? So tensile failure means this portion will try to break into two parts, this and this. As the failure takes place at this portion also and this portion also, we have to divide the area by 2, multiply the area by 2. So tensile failure will be equal to applied force divided by area. Now what is the area? If you see this cross section, so I'll again draw that cross section here with a different color. So if you see, if I take this cross section, right, it is nothing but a rectangular cross section. At the center there is a diameter of the pin. This portion will be subjected to tensile failure, this portion, right? If you see, one double I is there, hence there will be two area. Now what is this area? We'll calculate one area only. This is equal to d0, this is equal to d, as shown here, d0, this is d, right? And this is equal to thickness. In this case, this thickness is equal to, if you see, this is t2, right? So this thickness is t2. Now what is the area? d0 minus d into t2. This is for one portion, and then second area will be, hence it is multiplied by 2. So what will be the equation for this? 2 into d0 minus d into t2. That will be the tensile failure of the double I. So from this equation, d0 was known, d was known, and t2 is equal to, that is, thickness of this double Y was unknown to us, which we have assumed t1 is equal to 1.25 times of d, and t2 is equal to 0.75 times of d. So this 0.75 times of d is replaced here, d0 and d is known to us. We will again cross check the value of tensile stress. Again, this is equal to SYT upon factor of safety. SYT upon factor of safety is called as allowable tensile stress, and the value calculated from this equation will be calculated, known as calculated value of tensile stress. And for the safety of this dimension, which is written in the denominator for the area, the relation which we have to satisfy is that this value of allowable stress has to be greater than that of the calculated value. Then and then this dimension d0, d and d2 will be safe under tension for the double I. Understand? So again, this is tensile failure. Now we'll move with the next failure, crushing failure, bearing pressure of a double I. Now in this case, similarly, we have to assume that the central portion of the pin in the contact of the double I will be subjected to. So this one, or this one and this one will be subjected to crushing or bearing. So what is crushing? If there is relative motion, bearing pressure. If there is no relative motion, that is called as crushing stress. So crushing and bearing pressure both are calculated as applied force, either it is called as P or F, divided by which area we are taking in this case, projected area. So which is the projected area in this case? If we project this surface, what will be the area? If we project this particular surface, this particular surface is equal to T2 into diameter of the pin. So this is equal to T2 into diameter of the pin multiply by 2, as the bearing pressure takes place at 2 portion, so that is multiplied by 2. Understand? So T2 is known, D is known. Again we are checking crushing stress. It is SYC upon factor of safety, where SYC is nothing but 1.25 times of SYT for the double I material, and is divided by factor of safety, which we select from 3 to 5 or 3 to 6. This value will give us sigma allowable, and this ratio will give us sigma calculated. For the safety of design, again I'll repeat this number of times unless and until you remember it. Sigma allowable has to be greater than sigma calculated based on the basic of strength of material. If this equation satisfies, the dimension T2 D for crushing or bearing pressure will be safe. अगर ये 1 से लेता है तो we have to increase the dimension or we have to change the material. That we have to remember. Then next type of failure is shear of double eye. Now what is mean by shear of double eye? In case of shear failure, after the crushing, this pin will try to come out of this portion. Means there will be a shear failure from this portion. Component will come out like this, right? uh, like this shear will takes place, right? If you see, if I'll draw it again, a component will be removed from here, pin will try to come out of it, and portion like this will be come out, right? Which is having dimensions. This is equal to thickness d1 and this is equal to this time we have to find out if this is the outer diameter is equal to d0 and inner diameter is equal to d, right? Then d0 minus d will be this portion and this portion. D0 minus d, so what is shear failure? Direct shear is equal to applied force divided by area. The area will be equal to d0 minus d divided by 2 multiply by thickness d1. This is for this portion, multiply by 2 for this portion and for this portion. So from this equation we will get tau calculated by calculating this value, because force will be known, all force will be known on all the dimensions we have calculated earlier. Tau calculated, and then tau allowable will be equal to SSY upon factor of safety. That is, if shear stress is there, we take yield strength in shear. Yield strength in shear is again 0.5 times of SYT, where SYT is the yield strength of in the tension for this double eye material divided by factor of safety. This equation will give us tau allowable, right? So to avoid shear failure of the double eye, for these dimensions, the calculated value of the shear stress has to be less than allowable shear stress. That is the equation we have to remember, right? Allowable stress has to be less than calculated. Then and then the dimensions which we have assumed here or we have taken with the empirical relation and stress equation are safer. Understand? So this is about shear failure of the double eye. So as of now we have discussed 9 different equations, and which concludes the design of knuckle joint. In up till now we have discussed 9 relations, that are, we have first considered tensile failure of the rod of single eye and double eye. Then at the central pin for the single eye we have considered 3 failures. Then for double eye also 3 failures. So 3 for single eye, 3 for double eye, 6 failures. Tensile failure of the rod is 7 failure, and 2 failures for central pin. One is double shear and one is bending failure. So 7 plus 2, 9 failures are there. If we write down the stress equation and find out the dimensions with respect to these 9 equations, the dimensions of the knuckle joint are safe for the applied tensile force, right? So this is the way of designing a knuckle joint.